Hello everyone. Today I'm going to give you an insight into obtaining global reliable broadcast using partial broadcast channels in the asynchronous setting. My name is Diana and this is joint work with Martin and Chenda, and we come from ETH Zurich. So, to begin, broadcast is a fundamental primitive in distributed computing, and we can think of it as being a megaphone since it allows a party to consistently distribute a message to n recipients. Of course that actually there is no megaphone, and the parties are communicating through channels instead. Then, what makes obtaining broadcast difficult is that some of the parties involved, including the sender, might be corrupted. And therefore, the goal of a broadcast protocol becomes to help the honest parties obtain the same output. And moreover, in the case where the sender is actually honest, we want the honest parties to output exactly the message that the sender wanted to send. The model that is widely used in the literature is the Synchronous model, where we have to guarantee that any message sent through any channel of the network is going to be delivered within some pre-known amount of time. So, for example, we will know for sure that a message sent now is going to be delivered in at most 1 hour. The asynchronous setting, however, is more realistic but also more difficult. The only guarantee that we have now is that the messages are going to be delivered eventually, at some point in time. So a message sent now can be delivered maybe in 10 minutes, or maybe tomorrow, or maybe even next century. And what makes the asynchronous setting more difficult is that a party cannot know whether it has not yet received a message because the message is simply delayed, or because the party that was supposed to send it is actually corrupted and the message was actually never sent. About corruption, we consider a central adversary that controls the delay time of the messages, so he is the one that decides whether a message sent now is going to be delivered in 10 minutes or next century, and that can corrupt up to T parties, making them send wrong messages or not send some of the messages at all in order to cheat the protocol in a coordinated manner. Given this model, to achieve a synchronous reliable broadcast, a protocol has to satisfy two properties. The first property, validity, requires that if the sender is honest, then all the honest parties are going to eventually complete the protocol and output exactly the message that the honest sender wanted to send. And the second property, consistency, requires that if an honest recipient completes the protocol, then all the other honest recipients are going to eventually complete the protocol as well, and with the same output. This means that if the sender is corrupted, the honest parties don't have to complete the protocol. But if one of them does, then all of them have to do the same and to output the same message. This is different from the synchronous setting, where to achieve synchronous broadcast, all the honest parties have to complete the protocol regardless of the honesty of the sender. Now that we have defined what it means to achieve broadcast, we can talk about the threshold on the number of corrupted parties such that broadcast can be achieved. In the traditional model, so where the parties are simply communicating through channels, synchronous broadcast can be achieved if and only if T is less than 1/3 of N, and the same bound applies in the asynchronous setting as well. However, if we assume that we have a public key infrastructure, so that we have a system providing us with ideal signatures, then the bound looks much better in the synchronous setting, where now synchronous broadcast can be achieved regardless of the number of corrupted parties involved. For the asynchronous setting, however, the bound remains the same. And a fascinating line of works has investigated the impact of assuming BCAS channels among every group of B parties in a synchronous network. A BCAS channel is like a mini megaphone. It allows a party to consistently send a message to B-1 recipients. The first such result was done for the case when B is 3, so assuming 3 CAS channels, and it was shown that in this model, synchronous broadcast can be achieved if and only if T is less than 1/2 of n. And then the result was generalized to any B, showing that in a model assuming BCAS channels, synchronous broadcast can be achieved only when T is less than B-1 divided by B+1 n. A question that naturally arises is whether, assuming BCAS channels in the asynchronous setting can help us obtain a better result, or here the bound of 1/3 is simply impossible to overcome. And of course, if we can obtain something better, then what is a trade-off between the strength of the communication network, namely the size B, and the corruptive power of the adversary? We have addressed these questions in our paper, and we have provided impossibility and feasibility results. Firstly, for impossibility, we have extended the result from the synchronous setting, showing that there is no protocol achieving reliable broadcast secure against at least B-1 divided by B+1 n corruptions in the asynchronous setting. And then for feasibility, we started with a case with B is 3, and we have obtained a protocol achieving a synchronous reliable broadcast secure against T less than 1/2 of n corruptions. Considering the impossibility result, our protocol is optimal. Then we moved to the general case, so for a general B, and we have obtained a protocol that achieves a synchronous reliable broadcast, and that, considering the impossibility result, is almost optimal. And afterwards, we have obtained a protocol that achieves a slightly weaker version of broadcast, which we have called non-stop reliable broadcast. What happens is that the honest parties do obtain outputs as required in a synchronous reliable broadcast, but they might have to continue running some sort of background processes even after they obtain an output. This protocol is secure against T less than B-1 divided by B+1 n corruptions, and we have shown that the impossibility result applies to this case as well, making our protocol optimal. For the remaining time, I'm going to show you our protocol for the case when B is 3, and afterwards I'm going to explain the key idea for the general case. So, we are now working in the model N3, providing us with 3 CAS channels among any 3 parties. We are going to say that the party P mega sends the message M if P sends the message M to every pair of recipients through the corresponding 3 CAS channels. Then the corresponding notion is mega receiving. We are going to say that R mega receives the message M from P if R has received M from P through all the available 3 CAS channels, meaning through all the channels having R together with anyone else as receivers and P as a sender. A nice property of mega receiving, which is going to be useful when defining our protocol, is that if R mega receives the message M from P, then any other recipient R prime is going to eventually at least receive this message, more specifically to the channel having R together with R prime as receivers and P as a sender. We can now define our protocol. So in the first stage, the sender is simply going to forward his message by sending it to every pair of recipients through the corresponding 3-cast channels. So the sender is going to mega send the message M. Afterwards, on the recipient side, when a recipient mega receives the message M from the sender, he is going to notify everyone about it by mega sending the notification ready M. A recipient can also mega send ready M when he receives ready M from at least T+1 recipients, meaning that he has received it from at least one honest recipient. And finally, to complete the protocol, a recipient has to make sure that 2 conditions are met. The first one is that it has mega received the notification ready M from at least n-t-1 parties, and the second one is that it has mega send ready M itself. Intuitively, this would mean that all the n-t honest parties have mega send ready M. When these 2 conditions are met, then the recipient can output M and complete the protocol. I am now going to quickly explain why our protocol achieves a synchronous reliable broadcast when t is less than 1/2 of n, so when t is less than n-t. So firstly, for validity, we are going to assume that we have an honest sender that wants to send the message M. Our protocol guarantees that, in this case, no honest party is going to be able to mega send ready for a different message M prime. This means that eventually all the recipients are going to mega receive the message M from the sender. So all the honest recipients are going to eventually mega send ready M. This is enough to guarantee that the completion step is going to be eventually triggered for all the honest recipients, and therefore our protocol satisfies validity. And afterwards, for consistency, our protocol guarantees that if an honest recipient mega sends the message ready M, no honest recipient is going to be able to mega send ready for a different message M prime. This immediately implies that if an honest recipient completes a protocol with output M, no honest recipient is going to be able to output M prime. So all that we still need to show is that if an honest recipient outputs M, then all the honest recipients can output the same message. Our protocol guarantees that if an honest recipient outputs M, then all the recipients are going to eventually at least receive ready M from T+1 recipients, meaning that all the honest recipients eventually mega send ready M. And this is enough to guarantee that the completion step is going to be triggered for all the honest recipients, and therefore consistency is satisfied, which means that our protocol achieves a synchronous reliable broadcast. Now we are going to move on to the general case. So we are now working in the model NB, which provides us with bcast channels among every group of B parties. For the previous protocol, so when B was 3, our goal was to obtain a synchronous reliable broadcast for the case when T was less than 1/2 of n. But now we are going to work with a stronger communication model since B is now larger than 3, and therefore we expect to be able to afford more corrupted parties as well. So we are now working with a dishonest majority, which means that the honest parties might be forced to take decisions that are based only on inputs from the corrupted parties. And the idea that we are going to explore is that the more corrupted the sender seems, then the more parties the honest recipients should expect notifications from, in order to take a decision. We are going to refine this idea by defining the levels of confidence. In the first stage of each of our protocols, the sender simply forwards his input M to every group of B-1 recipients. So the sender is basically mega sending his input. We are going to split mega receiving into 1 receiving, 2 receiving, and so on. So we are going to say that R1, 1 receives the message M if it receives M from the sender through all the available BCAS channels. Then we say that R2, 2 receives the message M if it receives M from the sender through all the BCAS channels shared with one other recipient R1. We continue up to B-1 receiving. We say that R B-1, B-1 receives M if it receives M from the sender through all the BCAS channels shared with B-2 other recipients. And this notion of K receiving provides us with a nice property which is going to be helpful when defining the levels of confidence. So if we have a recipient that RK receives the message M, so that receives the message M from the sender through all the available BCAS channels shared with K-1 other recipients, R1, R2, up to RK-1, then we have the guarantee that any other recipient R is going to K+1 receive the message M through the BCAS channels that it shares with R1, R2, up to RK. This implies that it is possible that the recipients R1, R2, up to RK-1 are actually K-1 receiving the message M, while RK can only K receive this message. And now I'm going to explain the intuitive idea of the levels of confidence. So for message M, we are going to say that level 1 contains recipients that 1 receive the message M and therefore believe that the sender is honest. Level 2 is going to contain recipients that 2 receive the message M and have enough evidence to believe that someone on level 1 is honest and has already completed the protocol with output M. Then level K is going to contain recipients that K receive M and that have enough evidence to believe that someone on the previous level is honest and has already completed the protocol with output M. We continue this way until level B, which contains recipients that do not actually receive the message M, but have enough evidence to believe that someone on the previous level is honest and has completed the protocol with output M. More specifically, when a recipient 1 receives M from the sender, it places itself on level 1 and notifies all the other recipients about it by using all the BCAS channels that it has available. As soon as there are N-T recipients that have notified for level 1, then the sender might actually be honest, and this might be the N-T honest recipients. So all the recipients on level 1 are going to complete the protocol with output M. However, it is also possible that the sender was actually corrupted and that one of the parties on level 1 is corrupted, while there is an honest party that can only 2 receive the message M through the channels that it shares with each of the honest parties on the first level. So this party that 2 receives M is going to place itself on level 2 as soon as it receives the notifications from the parties on the first level. Since there are N-T seemingly honest parties on levels 1 and 2, the party on level 2 is going to complete the protocol with output M as well. And then it is also possible that all of the parties on the first level were actually corrupted. And the honest parties that went on level 2 have completed the protocol already, while there are some honest parties that can only 3 receive the message M. Then these parties are going to place themselves on level 3 as soon as they receive the notifications from the parties on the first 2 levels. When there are n-t parties on levels 2 and 3, so seemingly all the honest parties, then the parties on level 3 are going to complete the protocol as well with output M. And of course, it's also possible that actually all the parties on level 2 were corrupted as well, while there are honest parties that can only 4 receive the message M. So these parties are going to place themselves on level 4 as soon as they get the notifications from the parties on the first 3 levels. And when there are n-t parties in total that have notified for levels 3 or 4, then the parties on level 4 complete the protocol with output M as well. And the same idea is going to continue up to level B. Until now, we have only discussed when a party can stop waiting and make a decision. But we haven't discussed how we ensure that the honest parties are not going to output different messages. So let's assume that we have an honest party that K receives the message M, and another honest party that K prime receives a different message M prime. Then we make sure that if the corrupted parties complete the levels from 1 to K minus 1 for the message M, such that the dishonest party can place itself on level K, then there are not enough corrupted parties left to complete the levels from 1 to K prime minus 1 for the message M prime. So the honest party that K prime received M prime is not going to be able to place itself on a level for the message M prime, and it's going to have to keep waiting until it receives enough messages to place itself on a level for the message M and complete the protocol there. So that was it from my side. To conclude, we have shown that assuming BCAS channels can help us obtain a synchronous reliable broadcast secure against more than T less than 1/3 of n corruptions. And moreover, we have provided a quite complete characterization of the trade-off between the strength of the communication network and the corruptive power of the adversary. Thank you so much for your attention, and have a great day.